Okay, in this lecture, we're going to cover section 4.4. This is on indeterminate forms and L'Hopital's rule. So as we've seen, the idea of a limit is the basis of calculus. It's a fundamental concept in calculus on which it is based. And we've seen this time and time again, and we spent a lot of time trying to make this idea of a limit formal and precise. And we saw that we needed it to um, rigorously define what a continuous function is, to define what the derivative of a function is, to define things like vertical and horizontal asymptotes. So we've seen, hopefully at this point, it's very clear that this is a very fundamental concept to calculus, the idea of a limit. And so in this section, we're going to learn some techniques and some tricks on computing limits. And so far we've already seen quite a few tricks, some factorization tricks, and some multiplying by a conjugate. If you're taking the limit of a ratio where the ratio has a square root, maybe in the numerator and the denominator. But these tricks only go so far. There's a wide class of other uh, limits that are not accessible by these means. So we're going to learn a rule, this technique, this tool called L'Hopital's rule. And it's going to be very useful, and it's actually going to be um, based on the idea of a derivative. So you can use derivatives. So we use limits to define derivatives, and then in turn we can actually use derivatives once you have established the notion of a derivative. You can use it to actually compute limits, which is kind of peculiar. So let me share my screen. Hopefully you can see what I'm seeing. So let me open up the book. Oops. So we're in 4.4 indeterminate form. So the motivating example, I suppose you could say, is this example right here. It's capital F of X. And for whatever reason, I guess maybe we can think of this. For whatever reason, we want to know how F behaves near 1. What is the behavior of the function near 1? And maybe we're trying to determine whether or not we have a vertical asymptote, say, because vertical asymptotes can arise from roots of the denominator, right? So if you have a polynomial, like if you had 1 over, say, x minus 1, then this has a vertical asymptote at x is equal to 1, right? This is a point where it's not defined. If you take the limit as x approaches 1 from I guess, what is it, the right, you'd go up to positive infinity. And if you approach 1 from the left, you go up to negative infinity. I think the graph would look something like, let's see, it would look something like you shift over, this is 1 over x shifted over to the right, so you have a vertical asymptote at 1, and it would look something like this, I guess. So you could take a limit of this thing as x goes to 1, and you would see that, well, you'd have to do plus or minus. Actually, you can't, the limit as x goes to 1 doesn't exist. You have to do right-hand limits. And you can see that because from the graph, it goes to positive infinity on one side and then negative infinity the other. Well, you can take a limit, and you might wonder, oh, do we get infinity, or what do we get? And in this case right here, you get infinity on the right-hand side, negative infinity on the left. So you have a vertical asymptote here. And you might wonder the same thing about a function like this. Like, what's the behavior? It's clearly not defined at 1. If you plug in x is equal to 1, oops, sorry. If you plug in 1, you're going to get ln of 1 over 1 minus 1, and that's 0 over 0, and that's bad. This is not defined, so it's not defined at 1. But the function is clearly defined near 1, and it's possible that we even have an asymptote at 1. So we want to determine, we want to be able to deal with the limits like this, but we can't with the tools we have so far, such as factoring and multiplying by a conjugate, and that's because we have this ln in the numerator. So we need new tools to deal with this. Before we can, so and that tool is going to be L'Hopital's rule. And before I state that, we need some terminology. Notice that when you plug in one, we need some convention and some terminology. Notice that when you plug in one, you get 0/0. 0/0 is going to be called an indeterminate, and there are going to be many other types of indeterminate forms. And when we compute a limit, the idea is that if you get an indeterminate form, say you just, like, for example, with this limit right here, suppose we want to compute this limit right here. Suppose I just blindly plug in one. Let's just evaluate it at one. And I get ln of one over 1 minus 1, and I get 0/0. And as we noted up here, that's bad. So you get this indeterminate form. And when you just try to naively compute the limit and you get an indeterminate form, that's usually an indication that you need to use some sort of trick, maybe a factorization, maybe multiplying by a conjugate, or perhaps using L'Hopital's rule. So we want to first fully define indeterminate forms so that we can identify them easily and know when we need to use one of our tricks, or possibly even this new one of the known as L'Hopital's rule. So we have indeterminate forms. And so, for example, they're going to be of the form 0/0 or infinity/infinity. So if we don't have the only sort of limits that give us trouble are ones of this form or some variation of that, where you have f of x approaches 0 and g of x approaches 0 as x approaches a, like up here, right up here. So as x approaches 1, we have that ln of x approaches 0 and x minus 1 approaches 0. So this gives us an indeterminate form of 0/0. Now, sometimes you can get around these indeterminate forms to get a definite answer. So, for example, if we look at this one right here, we get an indeterminate form. So as x approaches 1, we have that x squared minus x approaches 0, and then x squared minus 1 approaches 0. So if we just, as I said, try to naively compute this limit right here, we're going to get 0/0. We're going to get this indeterminate form of type 0/0. But we can avoid this by simplifying the thing we're taking the limit of, and then taking the limit. Namely, we factor the numerator and the denominator, cancel some terms out, and now we arrive at something whose limit we can compute. This is we can compute this one right here. So you can either do some sort of factorization to compute a limit where you initially get an indeterminate form, or you can use multiplying by conjugates, or as we did, I think we did this limit here. I think we explicitly computed this limit. You can use a geometric argument to yes, that we did this one, and involved the squeeze theorem, I think. So we have some tools to at our disposal, but none of these are going to work for this one right here. This limit is going to require completely new ideas. And another one is this one as well. So not only can you take the limit as x goes to 1 of this thing, but you can take the limit as x goes to infinity. So as if you take the limit as x goes to 1, you can imagine that that's you're trying to determine whether or not you have a vertical asymptote at 1. This would be you're trying to determine whether or not you have a horizontal asymptote as x goes to infinity. So these are really important calculations, and they're going to be what all these limit calculations are going to go towards is determining the graph of a function. So we've already looked at curve sketching. We've looked at how the derivative tells us where we're increasing, decreasing, and where we can have local minimums or maximums, where we can have concave up, concave down, inflection points, all of that. That gives a really good idea of the shape of the graph. So we could do that whole analysis on this function, but then there's the only remaining question is, the only remaining question that you have in order to get a complete picture of the function, or a complete picture of the graph's function, the functions graph, sorry, is whether or not you have asymptotes, whether they be vertical or horizontal. So these are going to be really important calculations that we need to do. So we need to develop new tools. So how we're going to do that is by L'Hopital's rule. So yeah, so this right here also um, is another. This if you try to naively compute this limit, you're also going to get an indeterminate form. So as x goes to infinity, ln x goes to infinity, and also x minus 1 goes to infinity. Then you can just look at the graphs to see that. So what does the graph of ln look like? It looks something like this. So as x marches out to infinity, the graph kind of grows. It grows slowly, but it still goes off to infinity. So this would be ln x, and then 1 over x would just be your line, right? Shifted down 1 unit. The line going through the origin shifted down 1 unit. And again, as x goes up to infinity, this thing is just keeps going up to infinity as well. So you get infinity over infinity, which is going to be one of our indeterminate forms. So, um, in general, as they say, if we have a limit of this form right here, where both infinite f of x and g of x go to this positive infinity, or they both go to a negative infinity. They have to go to the same infinity. And if you get that, then you get what's called an indeterminate form of type infinity over infinity. Now, if you do get, say, the numerator, um, suppose the numerator goes to infinity, and then the denominator goes to negative infinity, that's not a problem, because what you can do is you can multiply by a double negative. And so you have ways of converting something like infinity over negative infinity to something as infinity over infinity, because if we're imagining, say, as x goes to infinity, f of x goes to positive infinity, but g of x goes to negative infinity. This will still give you an indeterminate form, just not directly. You need to do this trick where you multiply um, by -1 twice, and just leave a factor of -1 outside and a factor of -1 inside at the g of x, and this will ensure that um, negative g of x will go to positive infinity. So this will still give you indeterminate form. So there's ways of reducing maybe things that don't initially appear as an indeterminate form into something that is in fact a genuine indeterminate form. So we're able to compute infinite limits by some techniques. Like if I gave you something like this, you would have if you want to take this infinite limit, you can take x to the largest power and divide the numerator and denominator by that, and see you can then conclude that this piece right here goes to zero, this piece goes to zero, and you can actually compute the limit. But this is one technique for computing infinite limits, that is limits as x goes to infinity, but this type of technique is not going to work for this one again. So this is really a nice function to think about because it's a relatively simple function, but it's not amenable to computing the limit as x goes to infinity or goes to say 1 is not amenable to any of these techniques that we've developed so far. So as I said, we really need new techniques. So this example is just trying to illustrate or underscore this fact that we need new techniques. So what is that? What is this new technique going to be? It's going to be L'Hopital's rule. So it's going to help us to um, evaluate limits where we get indeterminate forms of type 0 over 0 or type infinity over infinity. So this rule is going to look kind of complicated at first, but it's fairly simple. So what it says is that if you start with two well, it's not fairly simple. It's not as, I don't want to say like insult your intelligence or anything, but it's not as bad as it seems initially once you've read it a few times. So let's just read through it first together. So you start with f and g are differentiable, and again, this is going to be basically every function that we're dealing with, so we don't even have to worry about that part of the statement. And then we're going to say that the derivative of g of x is non-zero on an open interval I that contains a, but maybe it's not, maybe it could be zero at a, say. So we and A is this point where we're taking this limit right here. Um, and you have a bunch of cases. So if you get that both limits go to zero, so this translates to 0/0, or if you get both limits go to plus infinity or minus infinity, and they have to go to the same infinity. So basically, you're going to get infinity over infinity. So in other words, if you have an indeterminate form of type 0/0 or infinity over infinity, then you can compute this limit by just taking the derivative of the numerator and the denominator separately. So you just take the derivative of the numerator and denominator separately. So this is really nice because when you take derivatives of, say, polynomials, it gives you a simpler function. So sometimes when you take the derivative function, it can be simpler, or sometimes it'll introduce pieces that can cancel with other pieces, and then you're able to compute a limit. All right, so we're going to look at a special case to see why this is true, and then we'll look at several examples to see how it works. So, and this is a pretty important special case. So we're not going to prove the statement in general, but what we're going to assume is that f of a and g of a are both zero. So we're going to assume all the conditions basically that our function is differentiable, that we're not zero on an open interval containing open interval I containing a, and that's just we need that assumption so that we can assume that this part right here is not zero because we don't want to divide by zero. That's all. That's the only reason why we're adding this piece in right here, this assumption. So we're going to assume we have such functions, and we're going to get maybe 0/0 or infinity over infinity, one of these indeterminate forms. But we're going to additionally assume this, that f prime and g prime are continuous, which is not that bad. Usually the functions that we're going to differentiate, their derivatives are also continuous. And we're actually going to assume that the derivative of the function at zero is, the derivative of g at a is not zero. We weren't necessarily assuming that in L'Hopital's rule. So, why is this the case then? So we want to show that we have such functions satisfying these other properties, then we're going to show that um, this limit right here is equal to this. So we're going to start with this limit and try to reduce it to this one right here. So what you do is, first of all, note that we're taking the limit as x goes to a of f prime of x over g prime of x. Now, this step right here, going here to here, is because f and g are continuous, right? We're assuming that. So if you want to take their limit, if you want to take the limit of a continuous function at a point where it is continuous, you just plug the number in, okay? Now, f prime of a, so what is that by definition? It's this limit right here in the numerator, right? It's the limit of this difference quotient. Same thing with g prime of a. What is it by definition? It's the limit of this difference quotient right here. Now, I have a limit in the numerator and the denominator, so I can just kind of factor it out right here. And then what happens is that now that the limit is on, I'm taking the limit of this whole fraction right here. I can cancel the x minus a with this x minus a right here. So I can cancel those terms out. And when you do that, you get the simpler quotient. And then one of our assumptions in this special case is that f of a and g of a are zero. So this term goes away and this term goes away, and it reduces to that. So it does in fact give us, we do in fact get the conclusion of L'Hopital's rule. This is a special case. As they note, there's a proof of the general case of the general version of L'Hopital's rule in Appendix F. I guess it's more difficult. I haven't really looked at it. I probably should look at it at some point. I don't remember how it goes. Um, but if you're interested in why it's true more generally without having these simplifying assumptions, for, assuming this special case here, I encourage you to look at that. All right, so how does this help us deal with this limit, this example at the beginning? All right, so let me open up Paint and then we can work through this together. In like real time, of course, is what I mean. So let's see, is Paint gonna open up? Yes, there we go. Okay. So this is example one. And we want to find the limit as x goes to 1 of ln of x over x minus 1. So here's the proof. So first of all, note as x goes to 1, we know that ln of x approaches 0 and x minus 1 approaches 0. So we get 0 over 0 indeterminate, right? So we get the indeterminate form, and then so that's like really the main part of L'Hopital's rule, right? There's a bunch of hypotheses that you need to satisfy in L'Hopital's rule, but the main thing is that you get this indeterminate form. And then also we know that ln x and x minus 1 are continuous. And we could say the derivative of x minus 1 is non-zero on an open interval containing containing the point 1. And that was like the other part, this also part. You need that these are continuous, or sorry, not that they're continuous, but they're actually differentiable. And they are, so there's no problem there. So these are differentiable. Oops. And the derivative of the function in the denominator is non-zero on an open interval containing 1, and possibly not at 1, but it's actually not, it's non-zero everywhere. Because the derivative of this is just going to be 1. So we satisfy all the conditions of L'Hopital's rule, so we're allowed to apply L'Hopital's rule. In practice, like if you're taking a quiz or an exam, you don't need to state this whole thing right here. I'm going to just give you functions that are differentiable, and the derivative of the thing in the denominator is non-zero on an open interval, etc., etc. You don't need to check that. All I need you to show is that you do in fact get an indeterminate form, and therefore you are allowed to apply L'Hopital's rule. So as long as you just state that, you'll get a full credit that you do get in fact get an indeterminate form, and therefore you're allowed to apply L'Hopital's rule. This part I won't require you to state formally, but I just wanted to, just for this first example, show you that technically you do need to show that you satisfy all the hypotheses of the L'Hopital's rule. All right, so now we can apply L'Hopital's rule. So by L'Hopital's rule, we can say that the limit as x goes to 1 of ln of x over x minus 1 is going to be, now the limit as x goes to 1 of the derivative of the thing in the numerator and the denominator. So I take the derivatives separately. I'm not doing quotient rule. I'm differentiating each thing separately. So that's kind of a nice fact. I don't need to deal with quotient rule, even though we are taking the limit of a quotient. All right, so now what's the derivative of ln x? That's just 1 over x. And then the derivative of x minus 1 is going to be 1. So what I end up with is limit as x goes to 1 of 1 over x, and that's just going to be 1. So what this shows is that I actually don't have vertical asymptote. Vertical, oops, asymptote at x is equal to 1. There's no vertical asymptote. So if you had no feelings as to what the graph of this function right here looks like, and so you had no idea whether or not it had a vertical asymptote or not. Now you know this doesn't have a vertical asymptote, so that's really it'd be really helpful in graphing this function. In fact, let me see if I can pull up a graph um, for this function. So we have, say, a graph of ln x over x minus 1. So what we should have is like a hole. I don't know if it's at x is equal to 1. So when you plug in, yeah, I guess it's not. Let's see. I can't really see with this graph, online graph. I've been using Wolfram Alpha, but unfortunately, what we should have is we should have a hole at 1 comma 1 on the graph, and it's not showing up on in Wolfram Alpha. And the reason why we have a hole at 1 comma 1 is because technically the function is not defined there. So let me see if I can use this other thing. So ln x by x minus 1. No, it's still showing up. That's weird. All right, well, so the graph, let me just plot it on here. So what the graph looks like, oops, the rough shape of it is something like, it looks so, oh, sorry. Looks something like you come down here, and then at 1 comma 1, you have a hole, then you go like this. And what that means is that because you're not defined at 1 comma 1, so it's 1 comma 1, you have, this is what's called a removable discontinuity. So in other words, you can redefine the function so that it is continuous there. So you could define this function to be a function from on the positive numbers to r, and you could define it to be f of x is equal to ln of x over x minus 1 if x is not equal to 1, and then just define it to be 1 when x is 1. And this will be continuous. Okay, let's look at another example. So we have, let me hold this down a bit more. All right, so this is example 2. So we want to calculate the limit as x goes to infinity of e to the x over x squared, e to the x over x squared. And so, so e to the x squared are differentiable, etc. They satisfy all the, and basically every hypothesis of the L'Hopital's rule. So the only thing we need to check is whether or not we get an indeterminate form. So as x goes to infinity, yeah, e to the x goes to infinity, and x squared goes to infinity, and that can be seen from the graph also. So the graph of e to the x looks something like this. This is 0 comma 1, and this goes off to infinity as x goes to infinity, and then you have x squared. It looks something like this. And yeah, that also goes off to infinity as x goes to infinity. So we get infinity over infinity. You don't have to technically draw the graphs, but sometimes it's helpful if you're unsure what the graph looks like. All right, so now we can apply L'Hopital's rule. So the limit as x goes to infinity of e to the x over x squared is going to be the limit as x goes to infinity. Now take the derivative, so of the numerator and the denominator separately. Oops. So the derivative of e to the x is just e to the x, and the derivative of x squared is 2 to the x. All right. Now, can we evaluate this limit? Well, no, because as x goes to infinity, we get e to the x goes to infinity, and 2 times x goes to infinity. Again, you can just look at the graph to the x. It's the line through the origin that definitely goes to infinity as x goes to infinity. So we have to do L'Hopital's rule again, and that's all right. Sometimes you will have to use L'Hopital's rule multiple times. So now you just differentiate the numerator and the denominator separately. Derivative e to the x is e to the x, and then the derivative of 2x is just 2. Um, and then I can factor out the 1/2, so I have limit 1/2 the limit as x goes to infinity of e to the x, and that goes to infinity. So what this tells us then is that this does not have, because we're taking a limit as x goes to infinity, this doesn't have a horizontal asymptote as x goes to infinity. I guess you could take the limit as x goes to negative infinity as well, although that might be a little bit difficult. We mean, actually we can't do that one quite yet. We will be able to do that one in a moment. So there's no horizontal limit, horizontal asymptote. So let me open up the book so you can see. So here we go. We have um, this is what the graph looks like, I guess, near zero, and you can see it goes off to infinity very fast, very, very fast. So what this tells you, I guess, is that actually what you can prove is that generalizing what we just did is that e to the x over x to the n is always infinity for all natural numbers n by, I guess you'd applying L'Hopital's, oops, I think you would have to apply it n times. L'Hopital's rule n times. And yeah, so x to the n. So what this shows is that um that x e to the x grows way faster than any polynomial, basically. So the rate at which e to the x goes to infinity, there's, in other words, like the x to the n, no matter how big x is, it can't dampen e to the x. It can't like pull it back down. So e to the x just goes off to infinity way faster than x to the n does for any x. So you just apply, and you can see that by applying L'Hopital's rule um, n times, and n times. And it doesn't matter how big n is. So let me see. Maybe I can. I don't even know if you'll be able to see a difference because EDX really is just gross so fast. So let's say plot e to the x over say x to the 100s. That's pretty big. Let's see. Wait, this doesn't even look right actually. Why is it flat on the bottom like that? Hmm. Let me just try this in decimals. E raised to the x and then divided by x to the 100. Wait, this is not right. Did I do something wrong? Hmm. I mean, they definitely got the same thing I did right here. See, you can see it. They compute, they use L'Hopital's rule twice, a second application, and they get negative infinity. So, but this seems to be showing that it goes to zero. Doesn't make sense to me. Wait, okay. So that's x squared. That's the one we're computing. What about x to the third? Okay. You can see a little difference. X divided by x raised to the third e raised to the x. Oops. I have x to the fourth. So it still goes off to infinity, and it goes off pretty fast. It is dampening it a little bit, but it shouldn't ever. It should still always go off to infinity. Let me do x raised to the 10. Huh. Maybe there's something. It must be a computer error. That's weird that it's doing that. It shouldn't be doing that. So 8. So, oh, I see. Okay. It does go off to infinity, but it does dampen it near zero. See, it takes a little bit longer for it to go off to infinity. So like so for x, when you have x squared, x cubed, x to the fourth, it basically goes off to the infinity at or below 10. Once you go off to x to the eighth, then you have to go out all the way to x to the 30th almost start seeing it go out to infinity. So when I did x to the 100th, it is going out to infinity, but it just takes a bit longer. You have to go further out. So it still goes out to infinity. So that means still it's true that e to the x is grows to infinity much faster than x to the n for any n. It might take you longer to go. You might have to go farther out for x to see that, but it still does. So x to the ninth, x to the 10th, 11th. Oops. I don't even know if I can zoom out far enough. Yeah, it starts to, the computer breaks down. What if I did x to the 50th? Okay. Oops. Yeah. And then x to the 40th. Yeah, so you can see it still goes off to infinity. Anyways, that's more time I want to spend than I want to spend on that problem. All right, so let's see. Let's look at another example. So this is an example of, let me see how many examples we have. Example 3. Let's see. Yeah, I guess we'll do this one. All right, so this is example 3. So we want to calculate the limit as x goes to infinity of ln x over square root of x. So as x goes to infinity, we get ln x also goes to infinity, and square root of x also goes to infinity. We know what ln x looks like, but maybe you don't quite remember what square root of x looks like. It's like a sideways, half of the parabola sideways, though. It goes like that. So it goes out to infinity kind of slowly, but it still goes out to infinity. All right, so it's not clear though. I mean, let's look at the graph of ln x. It kind of goes like that. It almost looks like it. It's just like the square root function starts at 0. This can go down to this can when you evaluate ln x, you can get really close to 0. It'll go down, as you can see. Um, but they both go to infinity fairly slowly, so it's not clear actually. Um, it might not be entirely clear when you take the limit of the ratio of these two, like does the which one goes to infinity faster? So if ln of x goes to infinity faster, then the limit of the ratio will be infinity. But if square root of x goes to infinity faster, then if it grows faster, then the limit could be 0. So let's see what we get. So it's not always clear what you're gonna get. So we know we can apply L'Hopital's rule because we get an indeterminate form. Should say that here. So this shows that we get infinity or infinity, so we can apply L'Hopital's rule. So we're taking the limit of ln of x over square root of x, which is the same thing as x to the 1/2. And now we're going to take the derivative of the numerator, so that's going to be 1 over x, and the denominator, so 1/2 x to the negative 1/2. And let's simplify a little bit. So we get x to the, well, so this 2, I can pull out, so it's a 1/2 in the denominator, so it flips into the numerator, and I can factor it out like this, and then I get 1 over x over, I guess, 1 over x to the 1/2. And if you, I guess you could multiply the top and the bottom by x. I guess, like I said, you could multiply the top and the bottom by x, and that would cancel the x in the numerator. And the denominator, you will get x to the, wait, did I do this right? Oh, it's sorry, something's not quite right. Oh yeah, it'll be square root of x, sorry. Yeah, so in the denominator will be square root of x. And oh, sorry, we're taking the limit as x goes to infinity. And now this is going to be 0. So the graph of square root of x, well, it's just a general fact that when you have 1 over x to a power and you let x go to infinity and say that power is a natural number, or it's a positive number, then that is going to go to 0. So maybe I'll just write that down. Recall, if you take the limit as x goes to infinity of 1 over x to the r, that's going to be 0 for, I think it's just any number positive. And that we certainly have, we satisfy that because we have r is equal to 1/2 in this case. So this is going to be 0. So that means that square root, the square root function goes to, it grows faster than ln of x. All right, let's see now. I'm going to skip example 4. You can read that through that if you want, and if you don't fully understand it, then you can we can work on it together. Well, let's see. And I'm gonna skip 5. I encourage you to read that one as well. So let's move on to other types of indeterminate forms. So the main indeterminate form is 0 over 0 or infinity over infinity. And there are going to be other indeterminate forms, but you can somehow are always able to reduce it. So for example, like if I had the numerator go to positive infinity and the denominator go to negative infinity, I could multiply by a negative. I could do a double negative to make sure that the numerator and the denominator both go to positive infinity. And you can do the same thing for negative infinity as well. If you wanted to both go to negative infinity, you'd multiply the numerator by -1, and that will change that. But we can have these other ones here. So let's look at these other ones. So this is called an indeterminate product. So it'll be something of the form 0 times infinity. So we're going to imagine that we have this limit holds, and this one does, or it could be negative infinity. So the limit of f of x as x goes to a is 0, and the limit of g of x as x goes to a is going to be infinity, or maybe even negative infinity. And we want to evaluate this product right here. So the idea is that you can, the part that goes to infinity, so if you know, so if, here's the fact basically, if g of x is going off to infinity, then 1 over g of x, and I think I've mentioned this in another video, then g of x goes to 0. So like for example, x, actually that's the example they're using right there. Anyways, I'll just go through it anyway. So for example, we know that x squared goes to infinity, and so that's going to imply, according to this fact right here, that 1 over x squared goes to 0. So the idea is to do like to rewrite your product like this or like this. It doesn't matter. And then that will give you, in this case, if you write the product like this will give you 0 over 0, and this one will give you infinity over Um, it could either be plus or minus infinity, and which is fine because you can just like factor out the negative or whatever you need to do to get infinity over infinity. Um, so if you know that f goes to zero, so that if you're assuming this, um, then one over f could be going to plus or minus infinity. It's not entirely clear. So let's look at this example to figure out how, because this is all kind of abstract, but let's look at how this type of manipulation works in practice. All right, so we're going to evaluate, oops, actually, let me write the example. This is example 6, and we want to evaluate the limit, the following limit, the limit as x goes to 0 from the right of x ln of x. So notice that x goes to 0 from the right. Well, what does x do? It goes to 0 from the right. So that's kind of just true. You would say it's vacuously or trivially true. But what about ln of x? Well, ln of x goes off to negative infinity. Okay. So we're basically in the that we're in the case where we have 0 times infinity in determinate form, right? But this can be reduced to either the primary indeterminate forms. It could be either 0 over 0 or infinity over infinity. And then we can use L'Hopital's rule. So the idea is you have these other types of indeterminate forms. L'Hopital's rule doesn't directly apply to them, but oh, I did not realize that I started that far over. Let me move this over. Um, you can't directly apply L'Hopital's rule to an indeterminate form like in 0 times infinity, but if you could reduce it to either one of these by doing some sort of manipulation, then you can apply L'Hopital's rule. So this is how there's actually two ways we can do this. And we'll do it both ways so you can see. And sometimes one way is easier than the other. So that we're going to take this limit of ln of x over, x ln of x. And what we're going to do is we're going to write it as the limit as x goes to 0 of ln of x over 1 over x. Okay? These limits are equal. So this thing right here equals this thing right here. And if you don't see it, just pause the video and look at it for a couple seconds or a couple minutes, however long you need, and try to see why these two are equal. And in this case, what happens? Well, when we take x goes to 0 from the right, ln of x goes to negative infinity. And then 1 over x goes to infinity, right? As x goes from the right, to 0 from the right. So we do have indeterminate form. We have this negative. That's not a big deal though. So we'll just kind of put a negative in there, insert a negative. So we get negative. We'll multiply by we'll do a double negative. And now what we get is infinity, negative infinity over well, I guess it didn't matter which one you did. You get negative infinity over infinity. Or you could have put the negative up here to make sure. Maybe I'll do that actually. It doesn't really matter. This will ensure that we get infinity over infinity if you don't like thinking about negative infinity. So now we can apply L'Hopital's rule. We've we have not used L'Hopital's rule now. We're just doing formal manipulation. We're just kind of doing some crazy algebra, crazy manipulation. But now we can apply L'Hopital's rule. So now we can apply L'Hopital's rule because we have infinity over infinity. And so according to L'Hopital's rule, we have to differentiate the numerator and the denominator separately. So we have the derivative negative ln x is going to be negative 1 over x, and then the derivative of the denominator is going to be negative 1 over x squared. All right, so this is good. So these negatives cancel, so you get negative ln of, sorry, the negative limit as x goes to 0 from the right. And when you simplify this, you're going to get the limit of x as x goes to the right, as x goes to 0 from the right. And that's just going to be negative 0, which is just negative. All right, I have to pause the video for a second and then I'll be right back. So let me see. Sorry about that. Let me share my screen again. So where were we? Let me see. Okay, so we had this limit of x times ln x as x goes to 0 from the right. We were able to rewrite it like this. This gave us negative infinity over infinity. So this is pretty close to the indeterminate form mentioned in L'Hopital's rule. We just need to tack on these negatives right here, and this would actually give us infinity over infinity. And then at this point, we can apply L'Hopital's rule. And when you do that, you take the derivative of the numerator and the denominator separately. So that gives you 1 over x, negative 1 over x, and then negative 1 over x squared. The negatives cancel. And then 1 over x divided by 1 over x squared simplifies to just x. And then when you take the limit as x goes to 0 from the right, you just get 0. So that would be one way you can rewrite the problem. And then another way would be to write it as this is an alternative way, and you could just take your pick which one you prefer. I don't think one is harder than the other, maybe. I'm not sure actually. Let's see. So another way would be to, so what the indeterminate form we were aiming for was infinity over infinity, but you could also do you could rewrite it like this, and this would give you 0 over 0, right? As x goes to 0 from the right, the numerator goes to 0, and the denominator does, because you know, because 1 over ln x, sorry, because ln x goes to 0, negative infinity when x goes to 0, 1 over it will go to 0, right? That was that fact I wrote there above. And then you can now apply L'Hopital's rule and differentiate each one separately. This one will actually be a little bit trickier. So in the numerator, you get 1. And then in the denominator, I guess the best way to write the denominator is ln of x to the negative 1. So then you do chain rule. And so the chain rule would say you get negative 1 um, times ln of, x, and then reduce the power by 1 times the derivative of the inside function would be 1 over x. And let's see, does this help? This is obviously a lot more complicated, so it's good to be able to try to manipulate this the thing you're taking limit of in multiple ways and just assess in your head, is this going to lead to an easier computation? So in this case, it's not. Let's see. This one it did not work out, so I don't think this is going to be easier. So I'm going to take this negative and just put it out here like that. And then, so what I have is 1 over x times ln of x all squared, and that's in the denominator, so it's going to flip into the numerator. And what you get is x times ln of x all squared. And oof, no, this is getting way more complicated. And now, because if I let x go to 0, this part goes to 0, but now this part's going to positive infinity. And yeah, too hard. I'm not even going to go through with it. So the point is, though, that you can manipulate this thing in one of two ways and get a genuine indeterminate form, the ones that we first looked at. There's 0, 0, 0 over 0 or infinity over infinity. But depending on what way you manipulate it, it might be a harder application of L'Hopital's rule. And so I'm not even going to bother going through with this. calculation because this is getting pretty nasty. All right, so I think we have, let's see, just a few more indeterminate forms, and that will be all we have. So let me pull the book back up. So the next type of indeterminate form is going to be infinity minus infinity. This is going to be called an indeterminate difference, but it turns out you can still reduce it to, in most cases, to an indeterminate form of type 0 over 0 or infinity over infinity. And we'll look at exactly what sort of manipulation it is. So that's going to be like a common theme, is like the primary is trying to reduce one of these indeterminate forms into the primary but the primary indeterminate form. So the primary indeterminate forms are 0 over 0, infinity over infinity, and we so far have seen indeterminate product, indeterminate difference, and in fact the next one is going to be indeterminate powers. It's like this. So, but the key is to somehow manipulate your express the thing you're taking the limit of and reduce it into one of the indeterminate forms like 0 over 0 or infinity over infinity. So let's look at this one though, indeterminate difference, see how to deal with that one. And so the reason why you can't really conclude anything from this type of difference is that like it says, there's this contest between F and G. Like in the case of F over G, you could get infinity over infinity, and the question is which one's going to infinity faster? So if F goes to infinity faster, then the answer is um, gonna be infinity probably. If G goes to infinity faster, then it could be negative infinity. But maybe they could both go to infinity at nearly the same rate that you would get a finite number as your answer. Who knows? You have to manipulate these and apply L'Hopital's rule. So let's look at this example here to see what sort of manipulation we need to do in the indeterminate difference case. So this is example 7. So we're going to take the limit as x goes to 1 from the right of 1 over ln x minus 1 over 1 minus x. And we want to evaluate. So whoops, I should have wrote that first. Evaluate this. So first of all, let me pull this down. So first of all, as x goes to 1 from the right, we have that 1 over ln x goes to infinity, right? And then because ln x, when ln x goes to when x goes to 1, ln x goes to 0. In fact, it's continuous at 1, so you can plug in 0. And so then 1 over it will go to infinity. And then 1 over x minus 1, we saw this, you just look at the graph, this is going to go to infinity as well. So we get infinity minus infinity. So we need to do some sort of manipulation to get one of the primary indeterminate forms. And what we're going to do is just combine the fractions. So we're going to go to take the limit as x goes to 1 from the right, 1 over ln x minus 1 over x minus x. And when you combine these fractions, I'm not going to go through all the steps. When you combine the fractions, you're going to end up with the limit as of x minus 1 minus ln of x over x minus 1 times ln of x. And you can see now when x goes to 1, you get in the numerator, you're going to get 1 minus 1 minus ln of 1, which is 0. So 0 minus 0, which is 0. So you get 0 in the numerator, and then you're going to clearly get 0 in the denominator as well. So we get the L'Hopital's, we get one of the primary indeterminate forms, so we can apply L'Hopital's rule. L'Hopital's. to this expression right here. Can't apply it to the original expression, but we can manipulate the original expression into something where we get the right indeterminate form. So we're going to differentiate the numerator and the denominator separately. So that in the numerator, we're going to get 1 minus 1 over x. In the denominator, we actually have to do product rule, but that's not bad. So the product rule says you take the derivative of the first term, which is going to be 1 times the second one, plus the derivative of plus the first function times the derivative of the second function, which is 1 over x. And then maybe, let's see, what do we get? And we actually get, so we actually get another indeterminate form. When x goes to 1, you get 0 in the numerator, and then you get 0 in the denominator as well. So we get that, we get another indeterminate form. So we have to apply L'Hopital's rule again. So let's see, in the numerator, let's see, what do I want to do? I'm going to actually, to make things a little easier, I'm going to multiply by the numerator and the denominator by x, which is fine. So I'm going to get x minus 1 over x times ln x plus x minus 1. And you still get 0 over 0 if you naively take this limit, so you get this indeterminate form. Now we're going to apply L'Hopital's rule. It's a little easier on here without having fractions within fractions. So in the numerator, you're going to get 1. In the denominator, you got to apply product rule for this first piece. So derivative of the first function times second function plus first function times the derivative of the second function. So x times 1 over x. And then derivative of x is just 1. And then derivative of -1 is 0. And now let's see, let's simplify this a little bit and see what we get. Can we actually compute the answer now? So we have ln of x plus 2, I guess. Yep. And yeah, we can apply, look, we can just actually compute this limit. We can, and the reason why is that this is continuous at x equals 1. It's a continuous function, right? 1 over ln x plus 2 is continuous. Not everywhere. There could be a point where ln of x plus 2 is 0, but that's not going to be at x equals 1. So the point is that it's continuous at 1. So you can just plug in 1. And then ln of 1 is 0, so we get 1/2. So kind of complicated, but yeah, but not terrible. Not terrible to do. Oops, I didn't want to do that. All right, so let's see, what else do we have? I'm gonna just skip 8. I'll let you go through that. And then we will do we'll look at these next indeterminate forms, the last type of indeterminate form, and we'll look at one example. So we have indeterminate powers. So indeterminate powers, it'd be something of the form 0 to 0, infinity to the 0, or 1 to infinity. And they arise from when you take limits like this. So the trick is to do basically a log, take a natural log. So you get rid of this g to the x, it'll become like a power or a coefficient. And the goal is to again take this particular indeterminate form, the indeterminate power, and reduce it to our usual indeterminate form of 0 over 0 or infinity over infinity. So we can take so we can apply L'Hopital's rule. So let me just, I'm not even going to bother actually going through these details because I don't know if they're terribly helpful. I'll let you read it, this little discussion here. But let's just look at an example. I think it's better to look at an example to illustrate how to deal with these types of indeterminate forms. So this is example 9. So we want to calculate the limit as x goes to 0 from the right of 1 plus sine of 4x to the cotangent of x. Oof, okay. All right, so what happens if we try to just quote unquote naively compute this limit? What happens is x goes to 0 from the right? Well, 1 plus sine of 4x approaches, well, this is a continuous function, right? So I can just plug in the number. I can plug in x is 0, and then so it's going to be 1 plus sine of 0, which sine of 0 is 0. So it's going to approach 1. And what about cotangent of x? Cotangent of x, as you approach 0, is going to approach infinity. So we're going to have um, 1 to infinity in indeterminate form. So if you're unsure why this is the case, I guess you can just consult the graph. So the idea is then let's take so we want to take this limit. So we're gonna let y be equal to the thing we're trying to take the limit of. Um Really what I want to do, I don't know if I like the way. So here's how we're gonna do it. I don't think I like the way the book is doing it. We're gonna call this limit L. So we're gonna say let L be equal to um the limit as x goes to 0 from the right. And we're gonna want to figure out what L is. But first what we're gonna do is compute a slightly different limit. So let's call L this limit that we're starting with. Oops, that's not right. It's sine of 4x raised to the cotangent of x. What we're gonna do is we're gonna apply. Basically, we're gonna like take the natural log of both sides and then exponentiate both sides at the end to like undo taking the natural log. So we're gonna take ln of L, and so it's gonna be ln of this limit. All right, that's terrible. Let me see if I can fix that. Cotangent of x. All right, now the natural log is a continuous function, and we know that the continuous functions they commute with limits in nice enough cases, and we're basically in one of those cases where uh things are nice enough. So this limit is going to be we can swap the natural log and the limit. So I guess you could say we can do this step because ln is a continuous function. And then what we'll have is the limit of, so now I have the limit of the natural log of 1 plus sine of 4x as cotangent of x. And now I can use um, the fact that this is a power and write it as a coefficient. This is one of the logarithm rules. So it's going to be cotangent of x times ln of 1 plus sine 4x. And then at this point, we had to ask ourselves, um, what kind of indeterminate form do I get? When x goes to 0, this is going to be infinity. In other words, well, as you can see, I'm not going to get 0 or 0 or infinity over infinity. I need a fraction, right? So the cotangent is the same thing as 1 over tangent, right? I want to introduce a fraction because I want to get you either 0 over 0 or infinity over infinity. So I'm going to rewrite this as 1 plus ln of 1 plus sine 4x, and then divided by tangent of x. All right, so now let's see what happens when x goes to 0. When x goes to 0, the numerator is gonna, it's a continuous function, so I can just plug in 0. So I get ln of 1 plus sine of 0, and that's sine of 0 is 0, so I get ln of 1, and that's 0, right? ln of 1 is 0. Now, tangent, what happens to the new what happens to the denominator? Well, tangent is continuous at 0. So I can plug in 0, and tangent of 0 is 0. So I get 0 over 0. So we're at a point where we can now apply L'Hopital's rule. So we can apply L'Hopital's rule. Might be a little complicated, but we can actually still do it. We can do it. We can apply L'Hopital's rule. So we're taking the limit as x goes to 0 from the right. So we're taking the derivative. We're taking the derivatives of the numerator and the denominator separately. So the derivative of ln of 1 plus sine 4x is going to be the derivative of the inside function over the inside function. Remember, that's how the derivative of natural log works. So maybe I'll write that on the side. So recall, if you take the derivative of ln of g of x, or say g of x is always positive, and it's differentiable, of course. So it has all the nice properties. The derivative is g prime of x over g of x. That's by the, yeah, you can see that by the chain rule. So in this case, we're going to have cosine, 4 cosine of 4x over 1 plus sine 4x, all divided by, now the derivative of tangent is going to be secant squared of x. And now at this point, why can you take the limit? Well, I don't think secant is defined even. Secant of x is the same thing as, what is it? It's oh, it's 1 over cosine, right? Oh, so this is fine. So now so secant, so let me say numerator. Well, that's kind of confusing because there's a numerator, there's these nested fraction. Let me put it this way. This thing right here, this thing right here, these are continuous functions at x equals 0. So now I can actually just plug in 0. So I only had to do L'Hopital's rule once. All right, so I get 4 cosine of 4 times 0, which is 0, over 1 plus sine of 4 times 0, which is 0, all divided by secant squared of 0. And that will simplify to 4. So I'll have 4 times cosine 0 is 1, so 4 times 1 is 1, over 1 plus 0, so it's just 1. So I have 4 in the numerator altogether, and then secant of 0 is 1, so it's 4. All right, so this is not done. We're not done though, because we took this is the natural log of the limit. This is the natural log of L. We're trying to figure out what L is, but that's not hard. We can just kind of undo things. So let me pull this down some more. So let me just write down what we have. So we have that the ln of L, our limit, is 4. But now we applied that natural log to the limit to compute the limit, and now we just exponentiate. We just kind of peel off the natural log. We take e to the ln of L is equal to e to the 4. But the exponential and the natural log are inverses. We have L is equal to the natural log. Sorry, we have L is equal to e to the 4th. But remember what L is. It's going to be the limit as x goes to 0 from the right of 1 plus sine 4x of cotangent of x. And so that solves it. So we figured out. So let me just kind of run through this really quickly because it's kind of a confusing problem. So the idea is you have this limit you want to start with, and you get the indeterminate form of 1 raised to the infinity by just analyzing the limit of each piece of this piece and its power. And you'll see that you get 1 up to infinity, so you get one of these indeterminate forms, like what is it called? It was called the indeterminate powers. This is one of the indeterminate powers. So here's the trick. You take, you call the limit L that you're trying to find, and then you take the natural log of both sides. Now the natural log is continuous, so you can switch the limit with the natural log, and then use the rules of logs to kind of simplify this right here. And then you'll get this, but you want to write this as a fraction because we want to reduce the problem to one of the basic indeterminate forms of 0 over 0 or infinity over infinity. And so you just put the cotangent in the denominator like this because cotangent is 1 over tangent. And then when you analyze this limit right here, you can see that you get, it's kind of complicated, but you can evaluate this thing, the numerator and the denominator, as 0, and you get 0 over 0. And now we can apply L'Hopital's rule. So this is where L'Hopital's rule kicks in. So you have a lot of setup first. You got like 4 lines of some manipulations you need to do. And now you can finally apply L'Hopital's rule. Take the derivative of the denominator and the numerator and the denominator separately. And then we'll end up with is a function which is continuous at that limit point 0. So just plug 0 in, and you'll get, when you simplify, you get 4. But as I said, this is not the limit. This is not L. We're trying to solve for the limit, or which we called L. This shows that ln of L is 4. So you need to exponentiate both sides. So this is exponentiate. This trick is called exponentiation. And then the E and the ln cancel to give you L is equal to ln of 4. And then that will finish the problem. You will have solved for the limit. You will have solved for L. Whoops, didn't mean to do that. Sorry. And so I think that's all. So there's another example, but and I'll let you work through that example 10. I think that's enough for now. This has been pretty computationally heavy. So let me stop sharing and then stop recording.